In this lesson, we will take a look at statements that contain an if-then structure. These types of statements are called conditional statements, and just like compound statements, they are dealt with in specific ways. Any statement of the form if statement A, then statement B is called a conditional statement. Statement A is known as the hypothesis, and statement B is known as the conclusion. Typically, A and B are simple statements, but they could also be compound statements or statements involving a quantifier. Let's explore some of the logic of conditional statements on the next few slides. First, let's try to determine when a conditional statement is true or false. To do this, we'll need some information about the simple statements A and B. Take a look at the conditional statement, if I have tofu, then I am happy. Can you identify the hypothesis? The conclusion? Here, I have tofu is the hypothesis, and I am happy is the conclusion. Let's see what happens if we know some information about the hypothesis and the conclusion. Suppose that we have tofu, and we are happy. How do you feel about the implication, if I have tofu, then I am happy? Do you believe it to be true? Sure. When we have tofu, the conditional statement says that we should be happy. In other words, when both our hypothesis and conclusion are true, if A, then B is also going to be true. Now, let's suppose that we have tofu and that we are unhappy, which might be the case for some of you out there. How do you feel about the implication, if I have tofu, then I am happy? Do you believe it to be true? Well, not really. When we have tofu, the conditional statement says that I should be happy, but we aren't. So in other words, if our hypothesis is true, but our conclusion is false, if A, then B is going to be false. Next, suppose that we don't have tofu and that we are happy. Again, this might be true for some of you out there. How do you feel about the implication, if I have tofu, then I am happy? Do you believe it to be true? Well, this one is a bit weird. If we have tofu, the implication says we must be happy, but the implication doesn't really tell us how we should feel if we don't have tofu. So in this case, since we can't prove the implication to be false, we're going to assume that it's true. In other words, if our hypothesis is false, it doesn't matter what our conclusion is, the overall implication, if A, then B, has to be true. On this page, I want to quickly summarize the truth values of the conditional statement, if A, then B, using a truth table. So just like we did for compound statements, we're going to have three columns, A, B, and our third column here is if A, then B. And we saw that if our hypothesis and conclusion are both true, our overall implication had to be true as well. However, if our hypothesis was true and our conclusion was false, this led to the overall implication being false. And finally, if our hypothesis was false, it didn't really matter what the conclusion was. The overall implication was true. So in other words, an implication is always true except in one case, the case where the hypothesis is true and the conclusion is false. Now that we have a better handle on conditional statements, you might wonder how to negate one. If you take a quick peek at that truth table, the answer is going to pop right out at you. It turns out that there's only one row where if A, then B is false, and that's when the hypothesis is true and the conclusion is false. So let's take a look at our tofu example again. When would this implication be false? Well, if I had tofu, but I was unhappy, I wouldn't be able to believe this statement. The statement is telling me I should be happy with my tofu. So the negation of our conditional statement is, I have tofu and I am not happy. In other words, if we have an implication, if A, then B, the negation of this conditional statement is A and not B. It turns into a compound statement. How would we negate the following conditional statement? Well, it might be helpful here to identify the hypothesis and the conclusion. 2 plus 3 is equal to 5 is statement A, or our hypothesis. A rectangle is a quadrilateral is statement B, or our conclusion. So based on the summary that we saw on the last slide, what we're looking for is statement A and not statement B. In other words, the negation should be 2 plus 3 is equal to 5, that's A, and a rectangle is not a quadrilateral, not B. There are 3 other conditional statements we can create using the simple statements A and B, and either switching the order or negating them. For instance, looking at our tofu example again, I could switch the order of A and B to get if I am happy, then I have tofu. This statement is called the converse of the original. What would we get if we negated the 2 simple statements, but kept them in the same order? If I don't have tofu, then I am not happy. This is known as the inverse of the original statement. And finally, we could both negate and switch to get if I am not happy, then I do not have tofu. This statement is called the contrapositive. Take a look at this statement. If 3 times 3 is equal to 9, then circles are not round. Try pausing the video and see if you can create the 3 other conditional statements for this example. To get the converse statement, we're going to swap the order of A and B. If circles are not round, then 3 times 3 is equal to 9. For the inverse, we're going to negate A and B, but keep them in the same order. If 3 times 3 is not equal to 9, then circles are round. And finally, to get the contrapositive, we need to swap the order and negate. If circles are round, then 3 times 3 is not equal to 9. Try creating the 3 other conditional statements for this example. If every square is a quadrilateral, then at least one integer is odd. If you need to take a quick peek at how to negate quantifiers, click up top. For the converse statement, I got if at least one integer is odd, then every square is a quadrilateral. Since we're going to be negating quantifiers for the inverse, let's identify them first. There are actually 2 quantifiers, a universal quantifier, every, and an existential quantifier, at least. So remember that our UQ needs to change to an EQ, and our EQ needs to change to a UQ. So for the inverse, I ended up with if at least one square is not a quadrilateral, then every integer is not odd. Now we've done most of the work to get the contrapositive already in negating our quantifiers. So all we need to do now is take the inverse and swap the order of our 2 statements. If every integer is not odd, then at least one square is not a quadrilateral. On our last page, there's a quick summary of how to create the 3 other conditional statements using the original conditional statement. Remember, for the converse, we want to swap the order of A and B. For the inverse, we negate A and B, but keep the same order. And for the contrapositive, we negate and swap the order. Of interest here is to note that the original statement and the contrapositive have the same truth values. It's also true that the converse and the inverse of the original statement have the same truth values too. So I'm going to leave that for you to explore. You can create the truth tables of these three statements and check that the contrapositive is the same as the original and the converse and the inverse are identical as well.
All right, my little epsilons, stay positive.